we have pictures. We just can't be bothered to like take them out of the. Now at this point, the pictures that we've got to go up are like a year old. So. Yeah, they were cuter then anyway. So
that's also messed up.
I'm not big on false praise. Okay. Here's you got your two possibilities. Yeah, that's true. Actually, they are adorable. Caleb is a lot cuter now than he was a year ago. He was a weird-looking baby. Now that he's grown, he's like grown into like the cute little kid. I'm sure he'll grow out of it. At some point, I'll bring in pictures of my kids or find a way to like show them on the screen or something. It really is. You'd be surprised.
If you're doing it wrong.
Just email them to yourself and then you can
Just post them on Schoology.
Make it our Schoology picture other than the
I'm not posting them on school. What?
What?
So we got to hear the notes yesterday. Make sure you have it, and then we have just step by step. So, or not so much step by step, but things to be. No. So, what's different about this and before when we were doing discs and washers, the radius was the distance from the axis of rotation up to the height of the curve. And the radius is still going to be perpendicular to the axis of rotation, but it's not necessarily going to be the height of the curve. It's usually just going to be x, or the distance from x or y to the axis of rotation. So the radius is not going to really have anything to do with the curve itself, the equation. The height is going to be perpendicular to the radius, so the height is now parallel to the axis of rotation, and that's going to deal with the actual function equation. And then when I draw that rectangle, that's always going to be parallel to the axis of rotation. That's where we're opposite from disc and washers. So in disc and washer land, when you draw that rectangle, that's perpendicular to the axis of rotation. In shells, we're running that rectangle parallel to the axis of rotation, because then once you spin that around the axis of rotation, that's how you get shells. And just remember big minus small. Nope. Could you just copy it? Okay, cool. Thanks. I believe they are on Schoology. Or if they're not, I can put them on Schoology. That's what I've been doing all year. That's like the last notes for the whole chapter. Can you finish the notes for the chapter? I believe it's Monday and Tuesday.
No, we don't do that. No.
Why? Monday is when I have everybody here.
Yeah, but you have us here. Do you have us here?
That's not my problem. So I was planning to do that on Friday.
But then, no. You know, it's fine. It's fine.
Yeah, I
No,
thought
it's
so.
not. No, don't back down. Wait, do you have like packets or something?
Yeah, I have packets that I've posted on Schoology. Would you like me to print out hard copies of them?
Yeah.
Okay, I'll try to make sure I can do that tomorrow and give them to you. Go away.
Wait, why don't they just phone the people?
Because I don't think that would work. They don't know where they are necessarily.
Y'all need like an app. You need like text on.
No thanks. Because then we would all get the text.
No, you would just enroll in the app.
They will mess it up.
You want me to sit that down?
That would probably work better than whatever they do.
I will make the app for you.
I don't.
Like everyone knew It's not like that.
All right,
They also had more staff.
there's your first example. Start working on making a graph and looking at it. Really, really impressed with how strong your pecs are. I see Armand like.
She did the same one, asked the same question to the same person. She already asked it.
I'm done with those for chapter 7.
I can write underneath it, and I won't have to write anything.
Correct.
Honestly, but who ever believes in you?
I know, that's why, because I don't
Look,
want to write underneath this.
This is my chapter 7 notes thing. I'm going to scroll.
Okay, if you end
That's the end.
if you end up lying, can you get a point?
Yes.
Okay.
There are no more notes in chapter 7.
No, because if I write examples underneath
I
it,
feel like
then I need to add
wait
to my
guys,
notes.
No, I'm not. We're done chapter 7 notes.
Would it count if you like say something right?
What?
Like say
Nah, because you could like fit that in. Usually that's just for you to listen and remember. And if you want to write it in, that's your business. Anything that I think is worth writing down, for sure, is written down. I mean, not even all of this stuff is worth writing down. That's why I italicize some things. What you generally shouldn't, except for like formulas. Because I don't know if I can get this not italicized. It turns out I can't. There. Nope. Better.
I like
E-L.
Yeah, you forgot the two L's.
E-L-L.
Yellow.
Kind of.
Huh. L. All right. So, step 1. What do we do?
Graph.
Graph. So, when you're doing areas or volume problems, area between curves, way back in 7.1, or any volume problem, graph. So we can see what we're dealing with. So you graph this x minus x cubed. How are we going to graph that? Actually, where do we need to graph it from who to where? 0 to 1. So we only need to go from 0 to 1. Where is this as x equals 0?
At 0 and 1.
And then in between, does it go up or down? Up.
It goes up.
Well, that's like 0.5. What's 0.5 cubed? Or 1/2 cubed? What's squared? 1/8.
Oh.
So we have a half minus an eighth. That's positive, right? So a half minus an eighth is 3/8. So we'll say this is 3/8. And does it really matter whether it's like a strict parabola or whether it's a lumpy thing? Not really for us. So I'll do that. Is that actually correct? Doesn't matter for our purposes. Really not important. So we want to rotate this about the y-axis. Yeah, about the y-axis. So up here, we have our y-axis, rotated about the correct axis. So I haven't made a big deal about this, but I always like draw a little arrow circling the axis about which we're rotating. Can I get through a class without being interrupted by people who also work here? So suppose we tried to do this with discs or washers. If we were doing this with discs or washers, then we would say our radius, we have a little r, we'd have a big R, and what would be a problem with this? They're both based on the same curve. And second problem, we'd have to do this in terms of y. That's not in terms of y, and getting that in terms of y is going to be terrible. So this is where we say, oh, discs and washers is not going to work. Or if it did work, it's going to be just absolutely horrendous to try to do it. So this is where we try to do shells instead. And with shells, then we have a rectangle running parallel to the axis of rotation. Our radius is still the distance from the axis out to there. From 0 out to this is along the x-axis. So this is just going to be x, where you are, minus 0, because that's the axis of rotation. So there's your radius. Radius r is just x. If we were rotating about the line x equals -1, then this would be x minus -1. So right minus left, you're at a position x along the x-axis. You subtract the axis of rotation on the left. That's x minus 0. You get x for your radius.
So how do we know that 1/2 is like the maximum of this one?
I don't.
So are we supposed to use y as the bound
Nope.
or not?
No, because we're doing this in shells, we get to do things in terms of x. That's why we're doing shells. So if we were doing this in terms of discs or washers, then our rectangle would be perpendicular to the y-axis, and we would have to do things in terms of y. And we could see, yuck, getting this in terms of y is going to be terrible. So we say, well, let's do shells instead. So then we run our this thing perpendicular to the x-axis, so that we're parallel to the axis of rotation. And now we're going to do things in terms of x. That's going to be a lot easier, both for this reason, and also, as you point out, for figuring out the bounds. Because is this the maximum? Probably not. I just kind of threw it up there for the sake of the graph. Nope. So they did get switched. Normally, when we rotate about the y-axis with discs and washers, we do things in terms of y. Now we're rotating about the y-axis, but we're going to do things in terms of x instead. Yeah, we just got to figure out, oh, is this the same equation?
No.
No, he had x squared. Big difference.
No, not the same equation. I mean, isn't it the same, like,
Yeah, so we're going to use that formula. We just got to establish what's r and what's h. No? Yeah. So big R is the distance from any one of these rectangles. So you're going to take these rectangles, and that represents one, like the edge of a shell, and you're going to integrate over the course from 0 to 1. So you have a shell here, and 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 a shell here. And each one of those shells is a distance x spaces away from the axis of rotation. So like this shell way out here is like 0.9 spaces away from 0. This shell is about 0.25 spaces away from 0. This shell is 0.5 spaces away from 0. So each shell is going to be a distance away from 0, and that distance is always, well, where am I on the x-axis? That's how far away from 0, that's the radius. If you rotate about x equals -1, then you have to x spaces plus 1, because you got to get all the way out to -1 over here. Since the axis of rotation is just 0, x minus 0. So it's always where you are on the x-axis minus the axis of rotation, which is just, in this case, x. Armand? We can put the shell anywhere we want. This is just kind of a generic placeholder shell so that we have something to draw and look at. So I drew it here. You might draw yours over here. It doesn't matter where you draw the shell. That's just a representation of any old shell. No? That wouldn't affect, if the whole region were like shifted up and we had this cut off under here,
say it's like.
it would still be kind of aligned to the x-axis. That wouldn't affect r, that would affect height. So that brings us to height. So height is the height of that rectangle, and that's just your y-job, x minus x cubed. So it fits for the rest of the day. Thanks. He interrupts my class and brings cake and doesn't bring any for me? Nah, I'm fine.
Can I have some?
Is it your birthday?
No, his birthday passed. It was in January. You didn't tell him the birthday.
Happy Ides of March. Hopefully you're not Caesar. All right. So we have volume,
Julius Caesar got stabbed in the back.
and in the front, in his head, and the legs, like all over. He got stabbed a lot. Thank you for the reaction. What's wrong with you? Maybe we'll get to this example. All right, so you've established R and H. Once you've got those, you shove them up into the volume formula with the integral, and the integral is going along the x-axis from 0 to 1, 0 to 1. You have 2 pi out front because we're back in rotation land, and then inside the integral you have R times H. That's going to be x times x minus x cubed. X times the quantity x minus x cubed. We're doing things in terms of x, so dx. And now you're on your way. So the heavy lifting, as usual, is on the front end with the making the graph, identifying R, identifying H. First of all, identifying, oh, this is a shell situation, not a disc and washer situation. Because as we go along here, we're going to start jumbling them together and say, hey, here's a situation, and then you have to figure out for yourself, should I use discs and washers or should I use shells? So you would say, I'm doing shells because doing washers would be awful. I find my radius, that's the distance of your representative rectangle from the axis of rotation, that's just x spaces. You find the height of the rectangle, that's the height of the curve, x minus x cubed, and then you put that into your formula. And you just got to then know, okay, what's my formula for shells? And once you've got that, you're on your way. You say this is x cubed minus x to the fourth dx. What do you get when you integrate? All right, 1/3 x cubed minus 1/5 x to the fifth. You plug in 1, you plug in 0, and we get 2 pi times what?
1/3 minus 1/5.
1/3 minus 1/5, which I think somebody has already said that's 2/15. And when, don't forget, you multiply by 2 pi, so we should end up at what, 4 pi over 15?
Yeah.
Yeah. So, ta-da! Once you get there, usually it's not so bad. It's getting to that formula that's the big deal. Armand?
So, yesterday, we got that
So yeah, dx is then the thickness of the shell. And then you're integrating over the course of infinitely many shells. So you have a shell right here that's right next to the axis of rotation, that's very close, and has a tiny height. And he has his thickness dx. And then you move the shell over, and he's a little bit further away, and so on and so forth. So the dx is the thickness of the shell, and then you kind of adding up all these shells with the integral over the course from 0 to 1. Yeah. So r is the distance from the axis to any given shell. Any given shell is going to be aligned with the x-axis. So r is always going to be x, where you are on the x-axis, minus the axis of rotation. Unless the graph is over here, and then it's the axis of rotation minus the x.
So if it were shifted, so if the job is like from 1 to 2, you would do x plus 1.
Well,
because from the.
oh yeah, so if we rotate around this line,
Took the 0 and flipped it and made it from 1 to
So just pick this whole thing up, put it over here, and then rotate around x equals 1. Then it would be x minus 1. Yeah. And if you're doing things in terms of y, it's the same thing but with y.
Well, what if you get the same volume?
Yeah, if you take up this whole thing, plunk it over here, and then rotate around x equals 1, you get the same volume. You get a different volume if you still wanted to rotate around the y-axis. Because now this whole area is farther away, so it's sweeping out a bigger circle around the around the y-axis. The r would still be x, yeah. As long as your axis of rotation is the y-axis, r is just going to be x. Or if you're doing it in terms of y, because you're rotating around the x-axis, the radius is just y. You only have to really think about r if you're rotating about some other vertical or horizontal line besides one of the axes.
How do you count the whole? Because if you're at one.
You account for the whole with just the bounds of integration.
Oh, right.
That's a good question, but yeah, that's taken care of. So in a lot of ways, shells is easier. I think shells is harder to visualize, but once you get it down and get the hang of it, I think the actual math involved is a lot easier. Armand? Okay. Let's look at probably just one more example for today. That's all I have planned anyway. And then you have homework. I think it's due tomorrow. And it's like 6 practice problems out of the textbook. What? I hope so. I had them assigned for after examples 1 and 2. So 1 and 3, they give you the picture. And we're rotating about the y-axis, so they're very similar to this. 5, same sort of thing, but without the picture. 11, same sort of thing. 16 and 18, they are now rotating about the x-axis. So, yeah, I think you guys will be fine. Picture! So, you graph that and pay attention to your bounds or how far along the y-axis you're going. That'll help you with making the graph. So we're only going from 0 up to 1. And if you plug 0 for y in, what's e to the 0? 1. And if you go all the way up to 1, what's e to the negative 1 squared?
1 over
1 over e. What's 1 over e? Is it bigger or less than 1? Less than 1. All right. It's about a little more than a third. Because e is 2.718288, and so on. So 1 over e is 1/2 more or less than 1/3.
Oh!
So it's about here. Right? No, we're going all the way up to here. What am I doing? Wrong graph. So that's about here. So I'm plugging in numbers for y, remember? So we're plugging in a number for y, plug in 0 for y, e to the 0 is 1. So we have the point 0 for y, 1 for x. You plug in the number 1 for y. You get e to the negative 1, that's 1 over e, that's about a third. So 1 for y, roughly a third for x. And then we're rotating this about the x-axis. And here's our region. So we want to take this thing from y equals 0 to y equals 1 and rotate it about the x-axis. And if we were going to do this with disks, we would draw our things perpendicular to the axis of rotation. And what do you notice about that rectangle as you move it across the space? It gets smaller. What do you notice about the top part?
It's a big rectangle.
It's a big rectangle until you get over here, and so the top of the curve changes from being flat to being the curve. So if we were going to do this with disks, we would draw our rectangles perpendicular to the axis of rotation. We would have to do things in terms of x, which we don't have in terms of x right now, and the radius would switch partway through, and we would have to find out where is that switch happening. So instead of doing it like that, we say, well, let's do it in terms of shells. So now we draw a rectangle sideways so that it's parallel to the axis of rotation. And now you can see no matter where you draw this, the left edge is always the x-axis, and sorry, the y-axis, and the right edge is always this curve. So that's not going to change. Our radius is the distance from that rectangle down to the axis of rotation. What's this always going to be? R equals y minus 0, because now this is just a location along the y-axis, so we're some height along the y-axis. That's how far we are from the axis of rotation. Y minus 0 is y. Our height is this thing, and because we're in terms of y, our height is the function. So h equals e to the negative y squared. And once you've got those two things, you can put them together in your volume equation and say volume equals 2 pi times the integral. We're doing everything in terms of y, so we're going from 0 to 1 up the y-axis, and then we have y times e to the negative y squared dy. Now, once you're here, what do we have to use to integrate this? U sub. Yeah. To make the U sub easier, it might actually be easier to put the 2 inside. So this is pi times the integral of 2y e to the negative y squared, because what should our u be? And then du is negative 2y dy. So when you have an exponential function, go ahead and let the exponent be your u, and then differentiate that, and you can say, oh, this is almost the same, I just need a negative, right? Negative, negative. Keep things fair and balanced, so throw negative inside and outside. And so we can say this is negative pi integral of e to the u du, right? So this whole thing is e to the u, and then negative 2y dy is du. What's the integral of e to the u? E to the u, so we have negative pi e to the u. Maybe switch back to negative y squared. And we're going from 0 to 1. So when we do this, and you plug in 1, you get negative pi e to the negative 1. And then you subtract negative pi e to the 0, which is just 1. So we have negative pi e to the 1 plus pi. Negative 1. Yeah. If you want to factor out the pi, I guess go ahead. So if you want to call this like pi times quantity 1 minus e to the negative 1, go for it. But that's your volume.
Oh,
I distributed the negative pi here, sorry. So, ta-da. So that's your volume. Using your shell method, and you can see that's a lot easier than doing the disks would have been, because disks would have required 2 separate integrals, and required getting the equation in terms of x, and required figuring out where the hell is this on the x-axis where we switch from this rectangle to this thing. So keeping your eyes open to, could I do it with this disks? Yeah. Does that mean I should use disks? Not necessarily. Maybe shells is a better method. I think for the homework tonight, mostly you just want to use shells just to get a handle on shells. And then tomorrow, probably we're going to start looking at comparison of when do you use disks versus when do you use shells.
shells
It depends on the situation. So I think if shells works nicely, shells is the way to go. So it's worth always thinking about, is shells going to work here? But there's times where shells is a nightmare, and you want to use washes or discs instead. Well, we'll see when we get there. We're out of time. I know that's a cop out. I'm not fluent enough in this to like come up with examples on the fly like that. When I've been teaching this for another 5 or 6 years, then I'll be able to kind of do that. I hope. Yeah, I come back and visit in 5 or 6 years and say, now I want to see an example.
After I graduated.
I've graduated college and I have nothing to do with math in my career now, but I want to know.
You think you'll still be here in 5 years? Or do you